All right, good afternoon. I'm Sean Rogers here at Zyxel North America. Today we're talking about Wi-Fi 101. So Wi-Fi 101 is not going to really talk about any of our products. Instead, what we do on this webinar is we look sort of into Wi-Fi, how it works, why we have some of the issues that we have when it comes to Wi-Fi, why Wi-Fi can be, sort of a really hard to troubleshoot beast at times. Um, We'll talk a little bit about the different Wi-Fi standards, and we'll give some best practices and some general guidelines here towards the end of today's webinar. So we'll start by just a quick summary on who Zyxel is for anybody that's watching this that isn't that familiar with us. We've been making computer networking products for over 30 years. We got started all the way back in 1989. We are a global company that serves over 150 different global markets. And we've got over 100 million devices that have been deployed over the years out in the field. So we'll start by talking about some of the Wi-Fi basics. So to begin with, there's the 802.11 standards. These are what became Wi-Fi later. So as you can see, 802.11 got started all the way back in 1997. So that predates, 802.11, 802.11b and G. And Zyxel actually did have 802.11 products. I remember when I joined the company around 2003, being able to find some of those old products in the warehouse that didn't have A or B on them because they were the original 802.11 based standards. And as you can see, things have moved on here. Things have picked up a pace quite a bit. You can see there's been a big lull there between 11N and AC and AX or Wi-Fi 6. And then we ended up with Wi-Fi 6E just a short time after Wi-Fi 6, and now we've got Wi-Fi 7 products on the market. You will notice, though, that I do show that 2024 for Wi-Fi 7. And the reason for that is that's because that's when this standard is expected to be ratified. So the final version vote is expected to be the end of this year. But there are products obviously already out there that are based on the initial 802.11be drafts. So that's something to keep in mind. And we'll talk a little bit more about Wi-Fi 7 later. So when it comes to the industry players here, there's the IEEE. So they're the guys that create those 802.11 standards. It's industry working group where engineers all get together and help create these different standards that we use for any sort of networking, not just Wi-Fi. 802.11 just happens to be that part of the standards that specifically address wireless technologies. There is the Wi-Fi Alliance. So the Wi-Fi Alliance came about in large part because there were compatibility issues when it came to different vendors and different devices. So while the IEEE tries to create a good standard, there's always room for interpretation when it comes to language. People interpreting some parts of the standard differently, which may result in different vendors implementing things differently. And then, of course, there's no body to enforce the standard, so vendors could always choose to ignore parts of the standard they didn't like for whatever reason. And so because of that, in the early days of Wi-Fi, there were compatibility issues between some of the different brands. So the Wi-Fi Alliance was created in part to help sort of solve that. So they're an industry group based around the idea of promoting sales of Wi-Fi products. So one of the things they did is they created their own certification. You've probably, if you've looked at a consumer Wi-Fi product, seen the Wi-Fi logo. It's gone through a number of different revisions over the years. This is the version that I'm most familiar with. And basically, they created their own testing to help sort of solve those interoperability issues. So in order to get that logo and put it on your product, you had to pass their testing that they do. In addition to that, they are marketers. So they're the ones who created the Wi-Fi name for 802.11. It's easier to say Wi-Fi than it is to, 802.11b, 802.11ax, etc. So that's where that Wi-Fi came from. And then around the time of Wi-Fi 6, they decided to rebrand Wi-Fi again. And instead of using 11N, 11B, etc., they decided to rebrand as Wi-Fi 6, Wi-Fi 7, and retroactively rename the older versions of Wi-Fi to make it easier for consumers to be able to tell what generation of technology they were buying. And then there's the FCC. So the FCC is the federal government. They control basically the radio waves. Wi-Fi uses radio waves, so we have to follow their rules when it comes from that. Now, for the most part, while the FCC sets the rules and in theory enforces them, most Wi-Fi type rules are enforced by just hoping that people follow the rules. I know there are a few, I guess more than a few years now, but a while back, one big vendor decided that they would just start shipping product that was well above the power output that was allowed by the FCC. And it eventually took another player in this space to sue them to force them to actually comply with the FCC rules. So while the FCC is there, and in theory, you can face some very large fines for not following the FCC rules. It's more of a pinky promise that we won't violate those rules. And for the most part, um, most vendors do a good job of sticking to what the FCC rules are. So now we'll talk a little bit about Wi-Fi. As I mentioned before, Wi-Fi is radio waves. There's really no difference between the radio waves used by a walkie-talkie or the radio waves used by traditional TV broadcast or radio broadcast and Wi-Fi, other than which frequencies are being used for it. So in general, if you're going to broadcast on radio waves, you need to get a license from the federal government that basically says here that assigns you spectrum that you can use, and you agree power output, you agree not to leak over it, stuff like that. But obviously that's a huge burden for people wanting to use wireless in their homes or in their businesses. So what happened is the FCC basically opened up sections of the Wi-Fi or the radio spectrum that don't require a license. So initially in the early days, it was 900 megahertz, so 902 to 928 megahertz. Then we got 2.4 and 5. And now more recently, they've opened up 6 gigahertz for people to use without a license. So now some key things when it comes to spectrum here is basically as frequency goes up, so the higher the frequency, traditionally, the more data that can be crammed into that. So you get faster speeds. That's part of the reason why 802.11a was faster than B, at least initially, was because of the higher frequency. It was easier to cram more data on there. Obviously, other technological tricks have come along that allow us to cram more data into the lower frequencies. But in general, as frequency goes up, the higher the quality. That's also why, for instance, if you're old like me and remember AM and FM radio, FM radio sounds better than AM radio, and that's in part why. And then the other thing here is frequency goes up, the shorter the range. So again, going back to the radio analogy, that's why AM stations, which are lower frequency, they have lower sound quality, but the signal goes farther. And also, if you use cordless phones, it's the same sort of thing. In-home cordless phone, those used to be 900 megahertz. So you could get on one of those, go outside, walk across the street to your friend's house and maintain a phone call. Whereas today's 5 gigahertz cordless phones, if you have a bigger house, you may not even be able to get coverage in your entire home. So the sound quality has gone up, but the range has gone down. And it's the same thing with Wi-Fi. This is just the way radio frequencies work. So when it comes to radio waves, we measure the power of the signal. So power is traditionally measured as dBm, decibel milliwatts. For every 3 dBm of power, you double the output power that's actually being used. So a 23 dBm access point has double the power output as a 20 dBm access point. So now, if you look at particularly at consumer products, you won't see dBm used. You will see milliwatts used instead. Whereas with business class products, you usually see everything done in dBm. So there's a couple reasons for that. At least in the early days of Wi-Fi, and for those of you still doing outdoor Wi-Fi, it's really easy to calculate your link strengths, your losses, and things like that because everything's measured in dBm. You could take or dBi, so you could take the dBm of your chip, the power output, add in the dBm of the amplifiers, add in the dBi of your antennas, and then subtract out the dBi losses from the cables and connectors to give you an idea of your total output power. So it's easy to add stuff together. And another key thing here is even though we're doubling the power, that doesn't mean you've doubled the range. But now when it comes to consumer side of things, the consumer side embraced using milliwatts instead of dBm. Why? Because those small power differences, as far as dBm goes, are huge differences when it comes to milliwatt power, right? So if you're advertising a product, your competitors are at 20 dBm, and your product is at 23 dBm, you don't want to say, hey, we're 3 dBm more powerful. It just looks like a little tiny number difference, 20 to 23. But if you use milliwatts, why, look at that, 200 milliwatts versus 100 milliwatts. It's so much more powerful. So for marketing purposes, that's why you will see consumer products using milliwatt power. But again, doubling power does not double range because signal drops off quite quickly. Those huge increases in power are really only noticeable at very short distances. And in a couple slides here, I've got the formula you use to calculate range to try to help you out with that. So some other things here, probably one of the most important things when it comes to Wi-Fi, and one that tends to get overlooked a lot, is signal to noise ratio. So it's basically the strength of the signal versus any other data or signals being broadcast on the same RF frequencies. So this is important. This is what's really going to determine the quality of your signal and how fast your connection is the signal to noise ratio. So to give you an example of this, or an analogy here, think about sitting at a small table in an empty room. You're talking to somebody directly across from you at the table, so you can talk at a normal voice level and you're both able to hear each other just as fine. Teleport that table and those two people into a bar on a Friday night at 10 p.m. And now you're not going to be able to talk to each other at that same volume of voice. Why? Because the noise has gotten louder, right? You've got other people in there now talking. You've got probably loud music playing, glasses clinking. So you end up having to either get closer to each other to talk, or you have to start shouting from another to hear each other. So that's the same thing. That's your signal to noise ratio. So when you're sitting alone in that room, you've got a good signal to noise ratio. When you're sitting in a bar at the same distance, you've got a poor signal to noise ratio. And then another common term you'll run into here is attenuation, which is just a measurement of how much a signal has degraded as it passes through different mediums. So as radio frequencies go, they are passing through stuff, and that stuff will basically absorb some of the power of those signals, causing them to degrade. So that's walls, that's people, that's furniture, that's just the air itself. So in fact, you'll find that, if you're testing stuff and you've got a nice low humidity, you can get better ranges than if you've got high humidity, because the water in the air will actually degrade the signal more than dry air will. So that's often a problem people run into with outdoor links, is that they'll have an outdoor link and it works perfectly fine for months until the rainy season comes and the humidity starts to degrade things, and then the rain itself will also degrade it and attenuate that signal. So this is how you figure out your path loss. So as you can see here, it is not a fun formula for calculating distance. You're much better off using third-party tools, where you can plug in your APs, like Ekahau or something like that, Heat Mapper, to be able to better give you an idea of the range you can expect where you are. But just to give you an idea here of some things here, a glass window will give you about 3 dB of attenuation, which will give you basically a 30% reduction in your range. So again, we've halved the power, but we've only got a 30% degradation in the range. Tinted windows that tend to have those metallic tints, those can have up to an 8 dB loss. So if you've got tinted windows or you've got screen windows, you may not want to put an access point in the window if you're trying to link buildings together. Depending on what those walls are made out of, you may get actually less loss going through the wall, especially on home buildings where you've got basically thin drywall on one side and maybe some thin wooden sheeting on the outside. But just in general, as things get denser, the more degradation you're going to experience. So when it comes to your Wi-Fi range, it's a combination of your signal strength, the signal to noise ratio on both sides, how much attenuation you're in, and the frequency being used, right? So you will get better distance with 2.4 than you will with 6 gigahertz. Something that tends to get overlooked a lot is that Wi-Fi is two-way communications. So your range is going to be largely established by the weakest member. So for instance, it's very common to have a business class access point with 500 milliwatts total output power or more. But you're often talking to phones, cheap tablets, things like that, where the output power on those guys is really, really low. So you're talking about something over here that, maybe, 30 dBm. And over here, you've got something where the dBm may be 6 dBm, 9 dBm. Um, so it doesn't, if you're trying to boost your range, boosting the power at the access point isn't going to have much benefit if the signal from your client devices isn't making it to that access point, right? The antennas on the access point can do some amplification of the signal, but only if that signal is getting to the access point. So generally, it's your client devices that are going to determine the range on your Wi-Fi network. And this is also why you run into issues with interference in office buildings, in apartments and things like that, is because the access points are able to send their signal a ridiculously long distance. Outdoors in a clean environment, this signal is going to go a mile or two and still be able to be picked up and detected and potentially cause interference. Obviously, if you're using it indoors, the buildings will help, reduce that drastically. But just to give you an idea of, just how far these signals can go. So that's something to keep in mind. Your client devices are really determining your range in your network. So just some general behaviors of Wi-Fi waves. Obviously, we call them waves, and part of that is because, when you chart them out two-dimensionally, they kind of look like water waves, and radio waves look basically the same. And they're basically doing the same thing. They're taking energy, and that energy is passing through a medium. In the case of water waves, it's the energy passing through the water. In the case of radio waves, it's the waves passing through the air and through various solid objects. But otherwise, they're very similar, and the behaviors you see with radio waves are very similar to the behaviors you would see with water waves. If you take a pond that's got maybe a little dock on it and you throw a rock out there and watch how the waves behave, it's very similar to what you will see with radio waves. So, you've got your source here. So this is where you would throw in your rock into the water, and the waves will ripple outwards. And then as they encounter various objects in that pond, they will behave different ways, right? So they can hit something and they can bounce off of it and reflect. So they can, if it hits it head on, it may reflect directly back to where it came from. But if it hits it at an angle, you'll get these other little ripple waves then bouncing back out in different directions. You can have the waves scatter and break up into multiple different waves going different directions. Waves have the ability to wrap around physical objects. And then in the case of radio waves, unlike water waves, they can pass through solid objects. So there's all this stuff going on with what starts out as a very strong signal can easily start bouncing off of different things and taking different paths. And this can cause interference issues and multipath, and we'll talk a little bit more about it in a few more slides here. So one thing here when it comes to Wi-Fi is that basically only one device can broadcast at a time. So in an RF environment, every one of your devices is taking turns on whose turn it is to broadcast. So it's similar to, again, if you've been on a road trip and you're listening to a radio station and you end up at night, getting out somewhere out in the boonies where you're between two different radio stations, both operating on the same frequency or on nearby frequencies, you'll often get that, it becomes unlistenable as the two signals sort of bleed into each other, cause weird artifacts, dropouts, things like that. That's the exact same thing that happens with Wi-Fi when two or more devices are broadcasting on the same channel. We call that co-channel interference. There are some exceptions to that when it comes to MIMO, which started being introduced with 802.11 AC Wave 2. And there have been improvements in that with Wi-Fi 6 and Wi-Fi 7. And we'll talk a little bit about that later. But just in general, basically each device needs to take a turn as to when it broadcasts. So the way that they came up with doing that all the way back in 1997 was basically this flow chart right here. So if you've got a Wi-Fi device and it wants to broadcast a signal, it will sense the medium. And all that means is it listens and says, hey, is anybody broadcasting on this channel I'm going to use? If somebody is already broadcasting, you'll back off. They use a random number generator basically to back off a certain amount of time, and then the process repeats until you get to a period where you listen, no one else is broadcasting, and then you get to broadcast what you want. Now, if two or more devices decide to broadcast at the same time, it will cause interference and both of them will drop their packets. So as you add more devices onto your wireless network, as a general rule, the lower your airtime utilization becomes because of how inefficient this is. There's no coordination between the clients. They're just all listening and waiting till no one else is talking to then jump in and do their broadcasting. And so as you add more and more devices, or you have more continuous traffic like video streaming or voice streaming, you're much more likely to have two or more devices decide to start broadcasting at the same time, right? You've got two devices that want to transmit. They both listen at the same time. They both hear no one else's, and they'll both decide to transmit. And then you've got your collision here, which causes issues. So that's why you actually see Wi-Fi performance degrade your as you add more devices. Your aggregated throughput will actually go down as you add more devices, and that's why. The other problem we run into with this is called the hidden node problem. So in this case here, we've got our access point here in the middle of the area. This blue circle is the area that it can hear and broadcast to. And we've got two different client devices here. So both client devices are within range of the access point, but the client devices are not within range of each other. So you run into this problem where this guy here is broadcasting to the access point. This guy wants to broadcast, so he listens to see, hey, is anyone else currently broadcasting? He can't hear this device, so he thinks that airtime is available and starts broadcasting. Access point then gets signals from both, they interfere with each other, and packets from both end up getting dropped. So that's our hidden node problem. It's something else that's very common on denser networks, that you run into this a lot more. So again, it's another reason why your Wi-Fi performance degrades as you add more wireless clients into your network. Now, the good news is Wi-Fi 6 and Wi-Fi 7 have sort of changed and provide some alternative methods for deciding whose turn it is to broadcast to help sort of solve some of these issues. The downside is it does require all devices on the network to support those features. So you need to have a network of just Wi-Fi 6 or Wi-Fi 7 clients to fully take advantage of it. But you are going to get some benefits of it, even if you have a mixed network. So another area I want to talk about here is the difference between data rate and throughput. So the way you measure the speed of a network connection has been done basically the same way since the 70s. I believe it's an IEEE standard. I could be wrong on that, but I believe it's an IEEE standard. And basically, it counts all data that's transmitted between two devices on the network. So that's what we would traditionally call a data rate. It is also known as the physical rate or the link rate, and it includes all the data that you want to send, and it includes all the data that goes into the overhead of making that possible. So in the days of wired connections, Ethernet connections, there wasn't much overhead. So there was very little difference between the data rate and what I'm going to call your throughput. Now, obviously, these terms can be used different ways. So this is the way I'm using them to keep it clear. And this kind of matches up with what I see out there. So data rate is what you're going to see on data sheets, product listings on Amazon, etc. And throughput is what you probably do when you first get a new device or you get an upgrade from your internet service provider, is you go out to something like speedtest.net or use an Ookla server or something like that, and you do a speed test. And so what happens is when people do that with their Wi-Fi products, they will find their throughput is often significantly less than the data rate. You can go to Amazon right now, pull up pretty much any wireless router or access point, and sort by negative reviews, and you will see most of the negative reviews are complaining about this difference. So throughput is measuring just the data you want to transmit and not including any of the additional overhead that goes into making it possible. So when it comes to testing, say, an Ethernet connection, there's a very little difference between the data rate and throughput because there's very little overhead besides the protocol overhead going on there. But when it comes to Wi-Fi and also home plug and other analog systems where we're transmitting over noisy environments, there is a ton of additional overhead that goes into making Wi-Fi work. And so because of that, it will change a little bit depending on which generation of Wi-Fi we're talking about. But as a general rule, there can be up to somewhere around 50 to 60% difference between the data rate that you see on the data sheet and the listing, and the throughput that you can see when you're doing a speed test, because the speed test isn't including this extra data. It's only considering the data that you want to send. So that causes a lot of confusion for people. And then, of course, there's other issues, right? If you're using a wireless client and you're, 2 rooms over from your router, you may not have the signal strength to achieve the maximum speed that router supports. In addition, and we'll get into this when we talk about these next few slides here, another issue you run into is your Wi-Fi client may not support the same speeds that your router does. So you get a mismatch there as well, which can result in your speed test being lower than the advertised data rate. So now we want to talk about, how do we increase speed? Now, this isn't what you would do deploying in a field. This is from a Wi-Fi engineering perspective. How do we get the faster speeds, right? We're using the same 2.4 and 5 gigahertz as we were using back in 802.11 and 11A and 11B days. So how is it speeds are so much faster today? How did we do that? So we'll go through it here. There's basically 3 main things that have contributed to the speed increases. Increase the encoding, basically how much data we can cram on there in a certain amount of bandwidth. We've increased spatial streams, and we've increased the bandwidth that's being used. So we're going to go through each of these, and we'll do it in reverse order. So we'll start here with increasing the bandwidth. So when we started out doing Wi-Fi, we were all using the 2.4 spectrum. And in the US, there are 11 channels available, 1 to 11. Now, the problem we run into here is these channels are very small. But the Wi-Fi channels that we're actually using, your Wi-Fi signal is actually using approximately 20 megahertz of RF spectrum. And the 2.4 gigahertz spectrum that's available for unlicensed use in North America is around 60 megahertz. So you've got a total of 60 megahertz, and each device is going to be using 20 megahertz. So one of the challenges we ran into here, one was these channels overlap. So people thought they had 11 different channels to choose from, but channel 6 here, it overlaps with 5, it overlaps with 4, it overlaps with 7, it overlaps with 8. So you only really have 3 channels you can choose from to avoid interference, assuming you control the whole network and can choose which access point each is going to use. So that's what we've got here. So one of the first ways we've tried to increase speed was to go from using 20 megahertz channels to using 40 megahertz channels. So we've doubled the bandwidth available, and that essentially doubles the amount of data we can send. So we're using a bigger chunk of the available spectrum. Now, of course, the problem you run into here is, again, there's only 60 megahertz available, and a 40 megahertz channel is using 2/3 of that. So as soon as you add some neighbor devices that are using the same 2.4 spectrum, or some non-Wi-Fi, some Bluetooth, whatever other type of 2.4 gigahertz device may be using, you probably are running into interference issues. You certainly can't have 2 or more devices using 40 megahertz channels at the same time. You will run into interference. So because of that, a lot of people, even if they've got their APs or their router set to use 40 megahertz channels, the good ones will detect that there's overlap and will automatically drop themselves back down to 20, even if you've set them to 40. But because of that, you don't get a lot of the speed increases in 2.4 that, had been initially advertised and promised. And that is why, starting with the later days of 11N, you saw a push to dual band access points and routers, where they would have 2 radios, a 2.4 radio and a 5 gigahertz radio. And the reason for that is 5 gigahertz has a lot more spectrum available to share. So as you see here, we've got, I think it's 26 channels, 26 20 megahertz channels that don't overlap. So in theory, you can have a lot more devices operating without worrying about interference issues, in theory. And this is also why there was a big push to using 5 gigahertz in cordless phones. So those people living in condos and apartment buildings, weren't overlapping and interfering with all of their neighbors. So going up to 5 gigahertz helps solve that for cordless phones as well as it does for Wi-Fi. Now, one of the challenges you notice here is that a big chunk of these channels are in sort of a, salmon color there, salmon and yellow. These are called DFS channels. So what happened is when the FCC decided to open 5 gigahertz up for unlicensed use, is that there were already people using 5 gigahertz that had licenses. So the way the FCC solved this was for creating a technology called DFS. And basically all DFS does is if you're going to be an unlicensed 5 gigahertz user in those channels that are labeled DFS, you are not allowed to broadcast on those channels until you listen and you make sure a legacy user is not already using those channels. So you tell your access point to broadcast on, channel 36. Or I think that's actually not a DFS. We'll say channel 64. That's DFS channels. So you can't just start broadcasting right away. You have to listen, make sure no legacy users are using it. Then you can start broadcasting. And then if at any point you detect and determine that a legacy user is now using that channel, you have to stop using it. Now, the APs, aren't very good at determining what is actually a real legacy user and what might be RF interference coming from something else. So even if you are in an area where there are no 5 gigahertz users using the same channels as you, you may still run into situations where your access point thinks there is a legacy user. So because of that, if you're using those orange channels, you may experience more drops because if that access point thinks that here's a legacy user, it will stop broadcasting. Now you can set it to automatically switch it to a different channel, but if that channel is also a DFS channel, then you have to listen and basically wait to make sure that new channel isn't being used before you start broadcasting again. So there can be a rather lengthy delay when it comes to switching channels. So because of that, a lot of users don't want to use that in a business environment, right? You don't want to be in the middle of a voice call and then suddenly have it drop for a second because your AP determined that there was a legacy user using that same channel now. The other problem you run into with these DFS channels is that it can add up to 6 months to the FCC certification process. So because of that, a lot of consumer equipment, including a lot of Apple equipment, doesn't support the DFS channels, or at least doesn't support all of them. So because of that, if you have users bringing their own devices from home, they often will not be able to connect to their nearby access point if it's using the DFS channel because that client device doesn't support it. This is one of the most common problems we run into on our tech support side is people calling in saying, hey, there's something wrong with your access point. We've got it set up in the meeting room, and when everybody comes in, there's 3 users who can never connect. And, it always turns out that for whatever reason, their client device, their laptop, their whatever, doesn't support DFS channels, and that access point that's in the meeting room uses DFS channels. So because of those 2 reasons, a lot of people choose not to use DFS channels. So now we go from having, 26 non-overlapping 20 megahertz channels to the point where we've just got 9, which is still pretty decent, right? You've still got 9. That's better than 3. But again, we want faster speeds, and we do that by doubling the bandwidth. So if we double the bandwidth to 40 megahertz, doubling our speed, we've now only got 4 non-overlapping channels. So we're almost back in the situation we were with 2.4. But again, we're still not fast enough. So the way we get it faster is we double the bandwidth again. So now we have 80 megahertz channels. So this was added with 802.11 AC. So now you see you've only got 2 non-overlapping channels that can be used. So if you're trying to use your access point, your 11 AC, 11 Wi-Fi 6, Wi-Fi 7 access point at full speed, you've only got 2 channels that have to be shared by every device that's using 5 gigahertz in your area. And of course, we wanted to get even faster than that, so we added 160 megahertz channels. Now, with 160 megahertz channels, you do have to use DFS. So again, if you've got a network where people are bringing their own products from home, they may not support DFS, so they may not be able to take advantage of 160 megahertz. And then Wi-Fi 7, they've doubled this again to 360 megahertz channels. So something to keep in mind, right, is if you're getting faster speeds, but in order to achieve these speeds, you may need to use parts of your spectrum you don't want to, and it may not be compatible with all your client devices. So the next area where we deal with increasing speed is with spatial streams. So as I mentioned earlier, radio waves can reflect, they can bounce off of stuff, they can break up into little smaller waves. So what starts off as a nice clean signal suddenly turns into a garbled, echoey mess over where your client is that's trying to listen to it. So this is something we call multipath, and this used to be the bane of Wi-Fi's existence. It was just this horrible thing to try to deal with. Now, at some point, people much, much smarter than me said, hey, you know what? We've figured out how to differentiate each of these different echoes and paths that the signal is taking. So even though it's the same signal on the same frequency, we can help differentiate them. So at first, what they did is they basically said, hey, we're going to be able to clear out these other unintended channels, these echoes, these reflections, and just focus on the main signal. So that gets us a nice, strong, powerful signal. Then some even smarter people said, hey, wait a minute, we can take advantage of these different paths and send different data simultaneously over these different paths, basically doubling or tripling the throughput that we can send out. So that's where MIMO comes in, multiple in, multiple out. It basically takes advantage of different antennas on your access point and on your client device, knowing that they are physically separated from each other and that the signals will take slightly different paths. So this allows them to send different data streams on each antenna, even though the antennas are using the exact same frequency. So rather than interfering with each other, we've taken this multipath issue and turned it into a benefit to increase our speed. So if your access point and your client device have two antennas, we can now send one stream of data on one antenna, one stream of data on the other antenna, and combine them together on the other end for an overall faster speed. So in this case here, this is 11N technology. Each spatial stream can send 150 megabits per second. So your overall speed for the client device is 300 megabits per second. Add a third antenna, now you've got 350 megabit spatial streams for 450 megabits total aggregated throughput. So that was pretty cool. So that was called MIMO. And then with 11AC Wave 2, we added MU-MIMO, multi-user, multiple in, multiple out. So it does the exact same thing as regular MIMO, but instead of having one client device receiving all of the spatial streams, you now use these spatial streams to allow you to send data to different clients simultaneously. So again, with 11N, your maximum speed per spatial stream is 150 megabits. So now you can send 150 megabit stream to one user and a separate 150 megabit stream of different data to a second user. Or if you had three, you could maybe do 3 streams or 4, depending on how many streams your AP can support. So that was how it's worked until Wi-Fi 7. So Wi-Fi 7, it's not supported on all devices, but Wi-Fi 7 now allows multiple client devices to send data back to the access point. So with 11AC Wave 2 and Wi-Fi 6, it was taking advantage of MIMO to send multiple spatial streams from your access point to the clients. And the clients still had to take turns sending data back to your access point. So with Wi-Fi 7, provided the client and your access point support it, you can now have multiple client devices taking advantage of MIMO to send data back to the access point simultaneously without interfering with each other. So when you're looking at data sheets, particularly for business class products, you will often not see the speed advertised or highlighted on the data sheet. Instead, what you will see is something like 2x2, 3x3, etc. So what this notation is this is how many spatial streams you support. So the assumption is you know that if it's an 11N AP, that each spatial stream is 150 megabits. So you can see that this device supports 2 spatial streams, therefore the total speed is 300. Or this device supports 3 spatial streams, therefore the speed is 3 times 150, 450 megabits. So it just kind of assumes that you know what each spatial stream speed is that that technology supports. So why are there 2 numbers? Well, the first number is how many antennas you have that you can transmit off of. And the second number is how many antennas you have that can receive a signal back. Now, when you're looking at routers and access points, these will usually be the same, 2x2, 3x3, 4x4. However, if you look at client devices, there will very often be a mismatch. Normally, the first number is much smaller than the second number. So basically, your client devices may be able to receive two streams, but it will only be able to transmit one stream back to your access point. So basically, the speed from the device to the access point is half the speed as from the access point to the client device. So it's very common to see 1x2 or 2x3 or 1x3 on client devices. And now in some cases, mostly on Cisco, but also now on our NWA 50 Pro and 90 Pro, you will see the two numbers here as normal, a colon, and then a second number. So what this is telling us is like 4x4:3 is telling us that there are 4 transmit antennas, there are 4 receive antennas, but you can only use 3 of them at a time. So realistically, from a performance standpoint, it's a 3x3, right? You use that smaller number, that's telling you the max you can use. So why do they do it that way? There are sometimes some slight benefits when it comes to dealing with interference and noise issues. Basically, you've got an extra antenna you can choose to use. If one of your antennas is getting poor reception, or the path isn't working, you could switch the signal over to your other antenna, and maybe it has a little bit better signal. So to put it all together, to find the maximum speed of your your device that you can achieve, you combine those 3 together. Find out how many spatial streams both sides support, find out your modulation type, and then find out how wide of bandwidth are you actually able to use. So again, depending on how you've got things set up and how the software's been implemented, some devices you may set it to 160 and they may automatically fall back to 80 or 40 based on environmental conditions. Not all vendors implement this the same way, so it depends. And then modulation type, this is really heavily dependent on the signal to noise ratio. To do these higher QAM modulations, you basically have to have really clean signals. So for instance, Wi-Fi 7 supports 4096-bit QAM, but the signal needs to be really, really good in order to actually be able to get that. Otherwise, it'll drop back bit by bit until it finds a level of encoding that works for your signal to noise ratio. So another common question we get is, how many devices can I put on one access point? And the answer to that is, don't believe what you see on the data sheet. Don't care who the vendor is, don't care if it's us, don't care if it's Ubiquiti, don't care if it's Cisco. That number you see on the data sheet is not a real world number. That number is just basically how much memory is in that access point that's been allocated to keeping track of connected client devices. In the real world, you will run into issues with your clients before you get anywhere close to that number that's on the data sheet. So, and this number, for the most part, with maybe a couple minor exceptions, for the most part, it doesn't matter what brand of access point you have. It doesn't matter how many clients are listed on the data sheet. It has to do with the Wi-Fi technology being used on that access point and the client devices that are being used. So you will run into issues that just have to deal with 802.11, whatever technology it is, 802.11, AC or AX or whatever. That will determine how many client devices you can get on there. Because as I mentioned before, as you add devices, they will start interfering with each other. So that's what's going to determine how many clients you can get on there. Is usually going to be, how fast are those client devices? How many spatial streams do those client devices support? And what are they doing on them? Are they checking email? If you've got a smart home plug that basically just sits there and every, 30 seconds sends out a packet to a server that just says, hey, I'm online, I'm here. You can get a lot of those on a network. But if you've got users that are trying to do, video calls, doing Zoom, you're gonna run into issues with your Wi-Fi coverage, after just maybe 20 or 30 users, depending on which access point you're using, what the clients are, how far away they are from that access point. So it's really hard to say and give you a number of how many devices I'm going to get on that AP. If you talk to our sales engineer, he's got some rules of thumb just based on his own real world knowledge, but those numbers are always changing as the way people use the network has changed. the types of clients that people are using. Sometimes you can start fitting more on there. Sometimes you just have to start reducing that number because, the technology people we're using are changing. Adding Zoom calls, during the pandemic makes completely changes the calculation versus before where people were primarily just using their computers for email and the occasional, audio call. So we've got an example here to sort of help you visualize this. So we've taken a scenario here. We're using a 5 gigahertz radio, 20 megahertz wide channels. And we've got users, and all of these users will be streaming a video stream that's 3 megabits per second. So it's like a 480, maybe a 720p video stream, depending on the compression being used. And the only difference between these three scenarios is how many spatial streams are supported. So you see here, if we use a laptop that supports 3 spatial streams and our access point supports 3 spatial streams, we're able to fit 34 users onto that wireless network with an aggregated speed of 100 megabits per second without having any issues with that stream. We change that laptop to a tablet, and we're assuming the signal strength is the same. And all we're changing here is the number of spatial streams. So we've removed a single spatial stream. So now our client devices only support 2 spatial streams. The number of users who can be on that wireless access point streaming that video drops from 34 to just 21. And the aggregated throughput drops from 100 megabits to 65 megabits. So again, same type of traffic, same signal strength, only difference is the spatial stream. Remove one more spatial stream, so we've now got a device that only supports 1 spatial stream. And now we can only fit 10 users on that same access point streaming that video before you run into issues. And obviously out there in the real world, not only do you have differences in spatial streams, you have differences in signal strength, you have differences in Wi-Fi technology. Some of your users may be Wi-Fi 6, some may be Wi-Fi 5, some may be Wi-Fi 4. So all of those sort of turn into a ridiculous number of factors to try to guess at to figure out the maximum number of users you can fit on that network. Okay. So the next thing I want to talk about is some of our different antenna technologies that Zyxel offers on our access point. So this is the only area where we're talking about, our products a bit. And I want to start by talking about our smart antennas. If you are familiar with Ruckus and you're familiar with their BeamFlex Plus, it's a similar technology. It's our take. It's very similar though. And basically, I want to highlight here code channel interference. So what is code channel interference? Code channel interference is basically, as we talked about before, for the most part, each user has to take turns broadcasting. So anytime you've got 2 or more devices broadcasting on the same frequency, you get code channel interference. So basically, you run into that problem I talked about before where you're between 2 radio stations broadcasting on the same channel and it just turns into a mess. That's what code channel interference is on the Wi-Fi side of things. And it doesn't have to be other Wi-Fi users or access points. It can be other sources of equipment that put out RF interference. It can be non-Wi-Fi devices that also share the 2.4 or 5 gigahertz spectrum. Now, one of the key ways that you used to traditionally deal with code channel interference is you would spend a bunch of time carefully planning out each access point you have and choosing which ones are going to use which channels so that they're geographically distributed. Obviously, that doesn't work so well in an office building where you're just one office in a building of lots of others that you don't control all of them, or if you're using a home user in a condo or apartment where, again, you don't control your neighbors. But assuming you're in the same, you're controlling the bulk of the network, that's how you would do it. Another way you deal with code channel interference is, as we remember, your access point is probably sending the signal a lot farther than the client devices are. So the client devices are right here. Here's your access point. Your client devices are here, but you're sending the signal all the way out here. So one of the things that you would traditionally do, and you may still need to do that in some cases, is turn down the power. So you drop the power on your access point so they more closely match your clients. And now you solve some of those overlap issues in the areas between access points. Now, the downside of this is you do lower your signal to noise ratio. So you may be trading poor performance due to interference with poor performance due to signal to noise ratio issues, just due to ambient noise. So the way we solve it with smart antenna is instead of having just an antenna in your access point, we have an array. And the array has the ability to use hundreds of different antenna patterns. So it's able to, in roughly real time, choose an antenna pattern optimized for each client that's currently connected to it. Now, our algorithm not only looks at where the client is in relation to the access point to help sort of focus the beam towards the client, it also looks for sources of RF interference and chooses an antenna pattern that basically allows it to ignore the signal coming from that interference source. So to use smart antenna, it requires nothing special on the client. It will work with any brand of client device. And it is not beamforming. It works perfectly fine with mobile users as they walk around. So as you see, it's near real time, so it can constantly adapt as users move around. So I want to go through a real world test that we did. So this was a hotel. I believe it was a hotel. Not condos. I'm pretty sure this is a hotel. And basically, we put an access point in each guest room. This is the type of hospitality access points that are a little bit lower powered, that are specifically designed to be put in one in each room or one in every other room to provide guest coverage. So this is what most of your mid-tier and higher hotels are doing these days, instead of the old way of just putting an access point in the hallway and trying to cover lots of rooms on one access point. So for this, we took our product, which at the time was a 1302, I believe, access point, and we took our competitor's product, a Ubiquiti, and both APs are roughly the same. They're roughly the same form factor. They're, I believe, both the same output power. The primary difference between our product and Ubiquiti was our AP has our smart antenna, Ubiquiti doesn't. So as you can see here, we're testing using 5 gigahertz, and we're avoiding those DFS channels. So because of that, we have to reuse some of those channels. So in this case, our test is done being used on channel 100. So as you can see, one AP on one floor, and then on the other floor, there's 2 APs using that same channel, but none are next to each other directly. So when we first do the aggregated test here, what we find with one AP turned on is we get an aggregated throughput of about 400 megabits per second. Ubiquiti is a little bit faster than us, marginally faster than us, 406 versus 404. And when it comes to airtime utilization, 67% efficiency. So no benefit really of smart antenna. Now we turn on the second AP and we rerun those aggregated throughput tests. So what you see here is with Ubiquiti, the aggregated throughput jumped up to 555 megabits per second, but our aggregated throughput jumped up to 785 megabits per second. So when it comes to airtime utilization, Ubiquiti was at 95%, basically as good as you can get. However, we were at 131% efficiency. So we were using more airtime than is, theoretically possible. So why is that? And that's because where the smart antenna comes in. The ability to choose an antenna pattern that allows us to ignore some of that interference and some of that noise coming from the other access point. So it allows us to actually achieve greater than the theoretical maximum airtime efficiency. Now we turn on our third AP and we see the same sort of thing here. Ubiquiti is only 544 megabits per second. We're up at over 900 megabits per second aggregated throughput. So again, our airtime efficiency went up from 131 to 155. And Ubiquiti's airtime efficiency actually dropped to 91% because the interference is causing some issues there that prevent it from, being as efficient as it could be. The other thing I want to draw your attention to here is how the data rates are distributed. You'll notice with smart antenna, each AP has roughly the same throughput, where with Ubiquiti, there are some huge discrepancies in the throughput per AP. Basically, this AP here is winning the battle for airtime, and the clients on this other AP here are suffering the most from the interference. I'm assuming this is the middle AP between the three. So just to show you, in a dense environment where you've got a lot of users or a lot of other access points, smart antenna makes a huge difference. So that's it for smart antenna. I want to now talk a little bit about Wi-Fi 6 and Wi-Fi 7. These are both new technologies. I mean, from talking to people, I know that, there's still a lot of questions about it, even though Wi-Fi 6 has in theory been around for a few years. There's still some questions with it. And obviously things are moving fast, right? We went from Wi-Fi 6 to 6E to 7 in a very short span of time. So let's talk a little bit about it. So 802.11ax was also initially marketed as high efficiency Wi-Fi. And then the Wi-Fi Alliance rebranded it as Wi-Fi 6. And I think most of you just call it Wi-Fi 6 these days. So some interesting things with it. Wi-Fi 6 was designed to work in theory on any frequency. So a lot of people didn't realize this, but if you have an 11AC access point or router, 11AC is only on the 5 gigahertz radio. Your 2.4 gigahertz radio is still using 11N technology, now rebranded Wi-Fi 4. So your 2.4 radio hasn't gotten any of those benefits that your 5 gigahertz radio has gotten. Wi-Fi 6 changes that. Now you can upgrade your 2.4 and your 5 gigahertz radio. So you get some really big benefits on the 2.4 side of things. It was specifically designed to deal with high density environments. So up to doubling the actual throughput at the same data rate. So if you had an 11AC access point and a Wi-Fi 6 access point, both with the same data rate, you would actually get double the throughput in theory through it in dense environments. So there's various technologies that came in there, higher QAM, OFDMA, basically the ability when you have those multiple users to be able simultaneously being broadcast to, you can chunk up the spectrum more efficiently. The ability to send data, multiple clients at the same time back to the access point, and something called spatial frequency reuse. So Wi-Fi 6 itself only got ratified in Q1 2021. A lot of the hardware that's out there is using older, cheaper chips. And because of that, some of the Wi-Fi 6 features are missing on that hardware. And just to give you an example here, features like upstream MIMO were only added to the Wi-Fi certification in 2022. So devices that were originally certified before that, don't have to support that feature and some other features as well. So just some things to keep in mind here. Not all hardware supports the full Wi-Fi 6 feature set. That includes our sort of SOHO products like the NWA 50 and NWA 90. They are missing some of those features. Also, some other vendors out there, for instance, Ubiquiti, on some of Ubiquiti's APs, they're advertised as a Wi-Fi 6 AP. Wi-Fi 6 is only on the 5 gigahertz radio. The 2.4 radio is still only 11N technology. Not all of their APs are that way, but some of them are, and there may be other vendors that do it I'm not familiar with. But just to give you an idea, we've got a little chart here showing you the Qualcomm Gen 1 chip versus the Qualcomm Gen 2. Basically, everything that we sell that's aimed at the business space, so anything NWA 110 and higher, is going to have the full Wi-Fi 6 feature set on both radios. So after Wi-Fi 6 came Wi-Fi 6E a little over a year ago, maybe a year and a half ago. So basically what happened is the FCC said, hey, 5 gigahertz is too crowded. No one wants to use these DFS channels. So they decided to open up a gigantic chunk of spectrum in the 6 gigahertz space. So up to 2.5 times more spectrum that's available. It allows you to have 7 non-overlapping 160 megahertz channels. You might remember with 5 gigahertz, you can only get 2, and only if you use DFS channels. So now with 6 gigahertz, you've got 7 non-overlapping 160 megahertz channels. So you really solves a lot of those interference issues, those co-channel interference issues that you get with 5 and 2.4, while allowing you to take advantage of the full speeds of 6E. And 6 gigahertz generally has no interference. So why do we say no interference? First one is there are no other devices that use 6 gigahertz other than Wi-Fi. There are no legacy equipment in your house. That may change in the future. The second reason for that is 6 gigahertz was licensed spectrum. And because 6 gigahertz frequency is higher, the signal from an outdoor user does not go into your house. It's not going to penetrate your walls or not very far. So because of that, you don't have to worry about interference from your neighbors. You don't have to worry about interference from legacy devices being used out there. So just to help you visualize here, here's 6 gigahertz. You can see it is bigger than 2.4 and 5 combined. So that's why there's been a big push to 6 and why 6 is probably the future for us. Now, the downsides of using 6 gigahertz, 6E, is the spectrum was used by licensed users, and those licensed users are still using it. So because of this, there is special technology that's required to use 6 gigahertz outdoors. You need to have what's called automatic frequency control, which uses a third-party service you have to pay for to basically keep track of legacy users and Wi-Fi users and allow you to dynamically change 6 gigahertz channels if a legacy user comes into the area. The unfortunate thing here is the FCC has not yet finalized those third-party vendors. They have provided some conditional approval, but because of that, we do not sell any 6 gigahertz products. And in theory, it is illegal to use any of our 6 gigahertz products outdoors. That will hopefully change here in the future. It's been taking forever for the FCC to finally approve those and finalize the rules for using 6 gigahertz outdoors. And part of that's because some of these legacy users are suing the FCC to block outdoor use entirely. There are some vendors selling outdoor 6 gigahertz using these conditionally approved 6 gigahertz third-party solutions, but who knows if they'll ever actually get fully certified or not. So we're waiting basically until the FCC finally starts fully certifying these third-party solutions and finalizes the requirements and how you need to operate outdoors. So we do not offer outdoors. The other challenge here is, of course, as frequency goes up, range becomes less. So if you're trying to cover the same area that you currently have in your network, you can't just swap out your existing APs with 6 gigahertz APs. The coverage will not be the same. You are going to have to add some additional access points to cover the same area. So those are the main things there. I've got some questions. So let's answer these questions before we move on to Wi-Fi 7. So Paul is asking, can Zyxel access points with 6E support so you function on 6 gigahertz while still supporting older 5 gigahertz products? So the answer is it depends on the access point you are looking for. So at Zyxel, we've got 3 Wi-Fi 6E access points we sell. The NWA 220 AX-6E and the WAX 620-6E are dual radio access points. So you've got one radio that supports 2.4 and one radio that can support either 5 or 6 gigahertz at 6 gigahertz functionality. So on those two models, you can use 5 or you can use 6, but you cannot use both at the same time. Now we also have the third AP, the WAX 640S, or yeah, 640S. And that one is a tri-radio. So it has one radio for 2.4, one radio for 5 gigahertz, one dedicated radio for 6 gigahertz. All 3 radios can operate at the same time. So if you want to provide coverage today for all 3 chunks of spectrum, the WAX 640 is the model you want to look at. Or jumping up to our Wi-Fi 7 AP, which is also 3 radios. So hopefully that answers that questions. Anonymous attendee, I will answer your question, but since we're at the end here, since we're not really talking about this, so I'll save that for the end. We're getting close, so don't worry, I'll get to it here in a second. So now let's talk about Wi-Fi 7, right? Wi-Fi 7 came out, you know what, less than a year after 6E as far as seeing hardware marketed on the streets, particularly on the consumer side of things. So what does Wi-Fi 7 do? It gets us a lot faster speeds. So in theory, the maximum speed a Wi-Fi 7 device can support is 46 gigabits per second. Now, of course, that's data rate, so actual throughput is going to be less than that, probably half of that, depending on the test and blah, blah, blah. But, you know, it's the same thing as any Wi-Fi. There's a lot of protocol overhead going into that. But still, it's, you know, half of 46 gigabits is still stupendously fast speed. I'm guessing most of you don't have any wired connections in your offices that support anywhere near those speeds. So how do we get faster speeds? The added 4096-bit QAM versus 1024-bit QAM on Wi-Fi 6 and 6E, which gives you about a 20% increase in your data rate. They've doubled the channels, so from 160 megahertz channels to 320 megahertz channels. So you might remember 6 gigahertz gives you 760 megahertz channels. So it gets you basically four non-overlapping 320 megahertz channels. And it's adding technology here that offers multiple link operation. So in theory, you can have a client device connect to your access point on 2 or more radios. So right now, your client device will connect to a radio, right? A Wi-Fi 6E product can connect to 6, 5, or 2. It will choose one of those based on its algorithm and the signal strength to decide which to connect to. With 7, in theory, your client device could connect to 2 or 3 different radios and then aggregate the data through it. So the benefits of doing this are obviously, as I mentioned, aggregate. You can aggregate your throughput across those 3 radios to get a faster connection. How we're getting up here to 64, but it can also be used to lower latency. And they do that is instead of aggregating data over these 3 different connections, you send the same data over all 3. And that lowers your latency because when we're dealing with Wi-Fi in these RF environments, a lot of packets are going to be dropped and need to be rebroadcast. So if you're sending the data simultaneously on 2 or 3 radios, if packets over here start getting dropped, instead of having to have them be rebroadcast, hopefully those same packets made it through on one of the other radios, so you don't have to wait for the rebroadcast, thus lowering your overall latency. And then another feature that's coming is called multi-AP coordination. It's the ability for multiple access points to be able to talk to each other and basically coordinate on how to divvy up and share the airtime if they're using overlapping channels. I'm going to skip this for a second here. So I'll just talk about it real quick here. So now another thing, and I don't think it's in this presentation, it's part of our Wi-Fi 7 presentation, is Wi-Fi 7 has not yet been ratified. So Wi-Fi 7, the final standard is expected to be out at the end of this year. So everything that's on the market now is based on the draft specification. So it remains to be seen, the hardware that's out there today, how much, if it will support all of the features in the final version of Wi-Fi 7 later this year. I'm hopeful that for the most part, it'll just be a firmware update. But, we ran into this with 11N and we ran into this with 11AC, where the first generation of products didn't support all of the features and it had to require a hardware switch to get those features. To make it even more confusing, there is expected to be a Wi-Fi 7 release 2 another year or 2 down the road after the first release. So that multi-link operation I was talking about, I'm pretty sure that's going to be in release 2, not in release 1. So it's something to know that that is something coming to Wi-Fi 7. If you go to trade shows or read the press, you may see people talking about multi-link operation, but I don't believe it's going to actually be officially part of the standard until release 2. And I don't believe any hardware currently out there currently supports it. So when do you want to use 6 gigahertz? Right? What are the benefits of 6 gigahertz overall? When do you want to use it? And we talked about the negatives. You can't use it outdoor yet, really. It doesn't have the range of 2.4 or 5. So basically, you would use 6 gigahertz in situations where you have really high density environments. It's going to be great in schools, conference centers, expo centers, things like that. It's also going to be great for applications that need to stream a lot of data. For instance, live uncompressed video streaming. That's something Wi-Fi 7 allows. Currently, if you want to stream video, you film it raw, you compress it, you send it over the stream, and then you decompress it and display it. So in theory, you're able to start sending uncompressed video, which will give you, that much lower latency for those video streams. It's also kind of ideal for doing wireless backhaul in an office. You may remember, what was it, 10, 15 years ago when Ruckus first hit the industry, they were really pushing wireless mesh. That was their big selling point, their big differentiator. And of course, most people don't use wireless mesh indoors today because of the issues with doing meshing. and it's really, pretty much only a consumer-only technology. So with 6 gigahertz, there's a good potential here that mesh may make a comeback in the business space, because with a 6 gigahertz backhaul, you don't have those interference issues. You've got a dedicated radio for sending the data, so you don't have the latency issues. So it starts to make business mesh in an office building um, a much more attractive solution than mesh has been up to this point. So that's another area where 6 gigahertz may have a big play. This is just reiterating again, the benefits for high density for 6 gigahertz. Now, of course, the biggest challenge we have with 6 gigahertz, whether it's 6E or 7, is that there aren't very many clients out there that support either of those. Those of you that are Apple users will know that the latest iPhones just now, last fall, added support for 6E. These still do not support Wi-Fi 7. If you want Wi-Fi 7 support, one of the only clients out there right now that's easily accessible is the Google Pixel 8 series, which again came out last fall. But it's going to be at least another year, if not more, before Apple users have 7 support. And if you look at like smart home products, almost all of those are still exclusively only 2.4 gigahertz. So it's going to be a while before you have a lot of clients that can support that 6 gigahertz space, unless you have control. If you're an environment where you guys also buy all the client devices, you may be able to control that and make sure everyone's using a Wi-Fi 6E or 7 enabled laptop. There are some out there that do support it, but for the most part, you're not seeing a lot of clients that support it yet. So that's going to be your biggest challenge, is you can't take advantage of 6 gigahertz if your clients don't support 6 gigahertz. And then also just on top of that, a lot of the client devices aren't going to support all of the features necessarily. So I fully expect a lot of lower end Wi-Fi 7 client devices to not support multi-link operation, for instance. That's probably going to primarily be a feature that's only supported on laptops, which have big batteries that can power 2 radios or 3 radios simultaneously, whereas a phone or tablet, you're going to burn through your battery too fast to support multiple Wi-Fi links at full speed. Okay, we're almost done, guys. So now on to some general best practices. Something to keep in mind is your access points in general are optimized, basically have one set of antennas in there, and they're optimized with the idea that they will be mounted on the ceiling above the area where it's going to need coverage. So in the real world, we don't always get to mount those on the ceiling. Sometimes we have to mount them at the wall. And when you do that, the antenna pattern is less than optimal, often sending signals up into the ceiling and down into the floor, not getting the horizontal coverage that you may want. Paul, I see your question. I'll get to that here at the end. Now Zyxel does offer something called dual optimized antennas. So those are access points that have 2 sets of antennas, one that's optimized for ceiling, one that's optimized for wall. So you can choose which to use when you install the AP. So that's something we have. Also, smart antenna helps solve for this as well. But if you don't want to spend the money for smart antenna, dual optimized is an affordable way to solve this issue. But if you're just using regular ceiling mount antennas, just do keep that in mind. They are designed for the ceiling, and you may run into coverage and interference issues if you mount them on the wall. So generally, basically, you want to mount your access point centrally located over the area to be covered, and as high as possible within reason to avoid obstruction. So basically what you're trying to do is you're trying to have a clean line of sight between the client device and the access point and minimize how many obstructions that signal has to go through. You don't want it going through your cubicles if you can avoid it. You don't want it going through plants or people. You want to minimize that so you get the best signal strength. Now, one of the challenges you run into, if you're in a building that doesn't have drop ceilings, is that ceiling may be 20, 30 feet up. That may be too high. You may end up into issues where the signal now is causing too much interference. So as high as possible within reason. Another thing to keep in mind here is drop ceilings. Most drop ceilings are just basically a bunch of fiberboard that's very porous. So because of that, there's very little signal attenuation. So if you have a customer that doesn't want you poking holes in their drop ceiling to mount your access points, you may be able to get away with just resting the access point on the top of the drop ceiling out of sight. Now, obviously, to do this, it depends on your building codes. That's plenum space. So your local building codes may not allow you to do that. But if they do that, that's a really simple solution for mounting your access points without having to poke holes in things. When you are mounting stuff up on the ceiling, you do need to take into account what other stuff may be up there, right? You've generally got a bunch of metal ductwork, lighting, conduit, pipes. So anything basically that's made out of metal is bad when it comes to Wi-Fi signal. So you want to, you don't want to mount it directly on your wood ceiling or whatever you're ceiling up there if right next to it some conduit and some vents and stuff. So you may need to drop it down a bit. And there are third parties who make drop down mounts that you can use to drop the access point below those obstructions while still having it plenty high. So when it comes to hotels, the traditional way of doing coverage is what we call umbrella coverage. Basically, you would mount the access points in a central area and you would cover multiple rooms, usually at least 4 rooms. In some situations, I've seen people covering up to 16 rooms with one access point. That was a great way of doing Wi-Fi 15 years ago when most people didn't have smartphones, when most people weren't carrying tablets, and you just had one guy on a laptop, which has reasonable signal strength, checking emails or browsing the web. Obviously that's changed. Most people now have at least 2, if not more devices per person that they want to connect to the Wi-Fi. Some of those devices are very underpowered, like cheaper phones, tablets, things like that. So because of that, this doesn't really work. You get a lot of complaints from your guests when you start doing this umbrella coverage, especially with a lot of hotels putting the bathrooms along the hallway, because now the signal's got to go through a wall. It's got to go through pipes. It's got to go through a shower. It's got to go through another wall and then travel halfway across the room to get to the user. And then more importantly, for that user's signal to get back to the access point. So generally the current trend in most mid-tier and higher hotels is to basically put an AP in each room, or at least an AP in every other room. So there are special APs specifically designed for these applications. These APs usually have pass-through Ethernet ports, including the ability to pass through PoE. So you can just run one Cat5e cable to the room, provide PoE power to the AP. Then you've got a cable out going to your IP phone in the room for the guest phone room, and then another cable coming out going to the TV for the IP TV stream to the TV set. So you're dropping a lot less cables into the rooms. It simplifies things, and you solve those connectivity issues that people would used to complain about. And if you are mounting APs in the guest room, a couple things here. You want a locking mount or something that's not obvious how easy it is to remove the access point, because guests will steal anything that's in the room that they can get away with. And then secondly, you want to be able to turn off the LEDs on the access point. You don't want to be tired from a long trip and have a blinking light directly above your head in the bedroom while you're trying to sleep. So just some other things here when it comes to hotels. When you're planning your coverage, the main area which you're going to be looking at is how many users per access point. The more users that you're going to likely have in an area, the more access points you need in that area. So rather than looking at square footage, look at user density. Use load balancing and client steering. And when you do this, you need to set up groups based on the geographic location. We had one of our installation partners who won't be named. They did a large hotel and they put the entire hotel into one load balancing group. So you had APs in the lobby trying to push users to unused APs that happen to be up on the 8th floor. So you want to break up your installs when it comes to doing the load balancing to keep them into the same geographic area. And you want to plan each area independently. So the room network should be, planned separately from the lobby, which should be separate from the hotel restaurant, separate from the pool, etc. And any area where you've got a lot of users, use smart antenna. So school strategy, again, the main thing you're focusing on here is the number of users and what they're doing with the Wi-Fi. Not every classroom is a smart Wi-Fi class or a smart classroom, and not every smart classroom does things the same. I have seen smart classrooms where basically the users, the students, are using their computers for taking tests and for submitting homework and maybe doing some Wikipedia browsing, and everything video wise or teacher's presentation is shown on either a projector or a smart screen in front of the classroom. I have also seen classrooms where instead of having everything shown on a smart screen in the front of the classrooms, any videos they watch are streamed to every single student's laptop, or where the teacher takes over and screen shares to every student's laptop. So obviously, if your teachers are screen sharing or sharing video to everybody's laptops, you need a lot more bandwidth than if you're showing everything on a smart screen and the students are just using their laptops for test taking and maybe research purposes. So take that into mind. If they're streaming video to everybody's laptop, you may need more access points in that area than if they're not. So as a general rule, once you get above 20 students, I suggest 2 access points per classroom. And if you get up to a point where you have 30 or more students per room, I highly recommend smart antenna. But again, that's going to depend on what they're doing on those laptops and how they're using them. So that's it as far as the presentation goes. Go ahead, if you have questions, use the question and answer interface to send some in. We've got 2 pending right now. I'll get to them in just a second. Just to highlight here while you're typing in your questions, most of our webinars are recorded and we upload them to the North America Zyxel channel on YouTube. So if you've missed something or you had to step away or you want to share something with someone, Zyxel America channel is the name of our YouTube channel. In addition to the webinars, we have video case studies on there. We have best practices, product announcements, things like that. And lastly, we do have user forums you can use. You can find it at forum.zyxel.com. So now I'll take a look at the questions here. So first was from anonymous attendee. What is the difference between NWA 50AX Pro and NWA 210 or 110 access points? So it's a good question. If you are one of our resellers, reach out to your salesperson. We have a battle card or reference sheet that highlights all the differences between the different models. I don't have one here that I can easily throw up on the screen, but the short version is the 50 and 90 series, or the 50 series is basically our Soho product. So it's got a 2-year warranty on it, versus lifetime and all of our business class access points. And it is missing some of the Wi-Fi 6 features. It doesn't have the full Wi-Fi feature set because the CPU just isn't powerful enough to handle some of the more advanced features of Wi-Fi 6. And it's missing out on some business features like WPA enterprise security, dynamic pre-shared key, load balancing, captive portal, things like that. So generally, once you get up into our business class APs, which are those with 3 digits, so NWA 110, 210, 220, and the 110 and 210 are sort of going away. The 220 is now going to be our new lower end model. Those have lifetime warranty. Those support the full Wi-Fi 6 feature set. Those support load balancing, captive portal, enterprise security, etc. So those are what the differences are going to be. Paul here is asking, did you say smart antenna is not the same as beamforming? If not, can you say a bit more about their differences? Sure. So beamforming is something that was introduced in 11AC. I forget if it was AC1 or AC2, but basically it uses similar technology to MU-MIMO to try to steer the signal towards where a client device is. So it basically does some modulations of the radio signal to try to direct it towards a client device. Which on the surface kind of sounds like smart antenna. The difference with smart antenna is a smart antenna is an antenna array. So you've literally got hundreds of different antenna patterns. So you're actually changing the physical antennas being used in the physical antenna pattern to optimize it for where the client device is. Also, smart antenna has the ability to work with any client device where beamforming generally doesn't. Smart antenna works with mobile users where beamforming really only works with stationary users, as it can take a while to tune the beam towards them when you're using the beamforming. And smart antenna doesn't replace beamforming, it can work with it. So it's a supplemental technology to beamforming. So I think those are the main differences there between them. Basically, you know, smart antenna is beamforming on steroids. Would be a good way to look at it. So that was it as far as questions go. I want to thank everybody here who showed up. I'll stick around in case someone's working on a question, but you can always email them to your salesperson. So again, I'm assuming you're one of our partners, you can reach out to Andy, Jacob, or David with any questions you have, and they'll then forward them to myself or to Marcus, our sales engineer, depending on what the question is. My email's up there on the screen as well, seanr@zyxel.com. You can always reach out to me. I'm not seeing any other questions coming in, so thank you for turning up. I'm going to go ahead and end today's presentation. Hope to see you at the next one.